Okay, I'm going to try to steam through this. 4.3, or 4.4 rather, for functions, no, calculus, my bad, 4.4, is all about the second derivative. Now, I want you to note something first. When I have a parabola and I take the first derivative, the graph of the first derivative is now a line with slope of 2. If I take the second derivative, which is just the derivative of the first derivative, I get a horizontal line where x is equal to a number, or sorry, y is equal to a number. Now, it's interesting to note because you will eventually do integrals where you have to take some known formula or graph and work backwards to what the other original function is. So I want you to note that. I also want you to note that when you take the derivative of a cubic, the first derivative becomes a parabola, and the second derivative becomes a line. So there's an interesting connection. Same with as you keep going, the first derivative becomes a cubic of a quartic, and the second derivative becomes a parabola. And these things are important. Now, the other thing about this chapter is about figuring out max or mins without having to take the slope on either side of it. And it turns out when the second derivative is bigger than 0, rather, in other words, when it's positive, you're dealing with a minimum. So let's say you find out that there's a minimum because the first derivative equals to 0 at x is equal to 2. You can then take the second derivative, plug in 2, and if the result is bigger than 0, you're dealing with a minimum. If the result is smaller than 0 of the second derivative when you plug in 2, you're talking about a maximum. If it's equal to 0, you've got to go back to original test and take the derivative on either side. When you find a local max or min where the first derivative is equal to 0 and the second derivative is also equal to 0 for that x value up here, let's say when x is equal to 2, you're probably dealing with a point of inflection like this. So this would be x cubed. And when you take the first derivative, 2x squared, and you find out when it's 0, you discovered 0 when x is equal to 0. But if you take the second derivative, which is 4x, and you plug in that 0, you get 0 again for the second derivative. So that's more likely that you're dealing with a point of inflection, and you should instead examine the graph on either side of the original, what you thought was a maxima or minima, and figure out what's going on either side. If the slope is plus here and plus here, you're dealing with a situation like that. If the slope is negative and negative, you're probably dealing with a slope like a point of inflection like that. Point of inflections are interesting too, because if you look at a ski slope, it gets steeper and steeper and steeper, and then at some point, it starts getting shallow again. That's called a point of inflection, and it's also where the second derivative of the function is equal to 0. So you can find points of inflections by setting the second derivative equal to 0 and determining the x value. Then you take that x value and you plug it back into the original function to figure it out where it's happening. So let's just jump straight to the examples, which I'll probably butcher. For each of the functions, state whether the value of the second derivative is positive, negative, or positive, or nothing, neutral. Okay, let's look at it as soon as I take a good picture of it. Here we go. Let's look at this first one. Right there. Okay. This is clearly concave down, right? Right to there. So that means the slope here is positive and it's negative here. It's positive on the left, negative here. And it means the second derivative, when you take it here, will be negative because the second derivative of a maxima for that x value of minus 3 will come out to negative, so that means the second derivative is still negative. Now notice this whole thing goes down and then turns and starts going the other way. There's a point of inflection that's probably there, halfway between A and D. B is still closer to A, so its second derivative is still going to be negative because it's still part of the concave down. However, when we get past the point inflection and reach C, we're now getting into concave up. So the second derivative here will be positive, and the second derivative here will be positive. Let's look at the other example, which is this one. This one's a little trickier, and what you have to do is continue the graph. So if this was a normal graph, it would look like this, obviously, if we just kept going. So we're dealing with concave down, right? Which means the second derivative of the concave down here would be negative. This is still on that same hill, so that means its second derivative would be negative. So that one's out of the way, and I'm just going to delete it for visual sake. Makes the other stuff easier. If you were to continue to draw this B, you would discover it's also a concave down, and it's still also on that point. It goes on forever downwards, which means we're still dealing with a concave down for point B, which means the second derivative for a concave down would be negative, because it would be a maximum normally here. Great, let's get rid of that, because it's visually it's going to make more sense. Now it's also clear that it's changed somewhere here. Somewhere here is the point of inflection. That this is mirrored by that on that side, and C is after that point of inflection. So if we get rid of the bottom point, we just work with the point of inflection. It's quite clear that C is part of a upward facing parabola, or concave up, and therefore the second derivative would be positive. Now we're going to go back to D. It's clear that D is part of a concave down, which means D's second derivative would be negative. Let's see if that was answering all the questions there. Yeah, they just wanted to know second and first derivatives. Let's go on to 2. We've got to do 2 and 3 together, because they want points of inflections on this one. This one, there's a good chance I'll screw it up, because one thing you're going to find for the complicated ones is second derivatives can get really complicated. Let's look at the first one, though. The first one's quite easy. Keep all your first and second derivative formulas around. And this is just the chain rule. Or they have a different term for it. I think they call it the product rule. 12x minus 15, but I mean it's really a version of the chain rule. So that's the first prime. Let's call that first prime. And keep in mind it's 3x squared. And then let's take the second derivative. It's going to be 6x minus 12. Notice the second derivative is a line and the first derivative is a parabola. And they say they want to determine the critical points. So they want to know if we're dealing with a maxima or a minima or an inflection point. Now, this original thing is a cubic with a positive coefficient. That means it could look like this. It could have 2 maximas and a minima. It could even have, or it could have a point of inflection, where like x minus 3 cubed would have a point of inflection here at 3, at x is equal to 3. So you have to figure out a little bit more what's going on, but there's 2 possibilities. So the first thing you do is you set this equal to 0. And the first thing you notice is I can factor a 3 out of it. And you're left with x squared minus 4x minus 5, which means you're actually dealing with x minus 5 and x plus 1. Those are the factors there. Which means if I set that to 0, I will discover that I'll get a 0 at 5 and I'll get a 0 at minus 1 when x is equal to minus 1, which is great. That means I'm actually dealing with a bump like this. If I came up with 2 critical points for this parabola, it means the shape of the cubic is going to have 2, maximum and minimum. Now, as it turns out, because I know my cubic graphs, I know that this is automatically a maximum, and this is automatically the minimum. But let us instead use the second derivative rule, and we're going to plug in minus 1 here. So we get 6 times minus 1, which is minus 6, minus 12. It's clearly a negative, right? Minus 18. It doesn't even matter. The number doesn't matter. It's clearly a negative. When the second derivative is a negative, which it is here, we're dealing with a maxima. So that's obviously, we already knew that, but it helps to see it. Now when I plug in a 5 over here into the second derivative equation instead, I'm dealing with 30 minus 12, positive 18. So over here, I'm clearly dealing, because the second derivative is positive, a minima. So that means when x is 5, and I want the y value, so I plug it into here. 5 times 5 times 5 is 125. Minus 6 times 25 is minus 150. So I'm dealing with minus 25 so far. Minus 15 times 5 is minus 75. So I'm dealing with minus 100. Plus 10, I'm dealing with minus 90. So that means when x is 5 over here, the y value is minus 90. Then when I plunge in minus 1 over here, I get minus 1. Minus 6, that's minus 7. Plus 15, that's plus 8. Plus 10, 18. So I'm dealing with a spot minus 1, 18. That has nothing to do with the second derivative, by the way. That's just the point when I plug it into the original function. So now I know the exact points of my maxima, the exact points of my minima, and I've proven it with the second derivative, and I can safely graph it as well. You discover when the max minima are exact numbers like this, the x-intercepts are not. That's really generally speaking. So you won't find a strong connection between whole numbers here and whole numbers at the x-intercept. There's probably some exceptions, but generally speaking, that's true. Now, determine the points of inflection in this part. So in a cubic, I already know there's only going to be one point of inflection. That's because this whole graph is turning down here. This whole graph is turning up here, and I'll do it in red so you see. I already know this whole graph is turning down here, and I also know this whole graph is turning up here. So I know there's only going to be one point of inflection. Out of guess, I'm going to say it's somewhere between minus 1 and 5, which is 2. So I'm going to guess that the x value is 2. But what you do is you set your second derivative instead to equal to 0. Oh, I got it right. So that means 6x is equal to 12, which means x is equal to 2 at the inflection point. But you've got to plug it into the original equation to figure out the y value. So 2 cubed is 8. Minus 6 times 4 minus 24. So what's 8 minus 24? It's minus 16. Minus 15 times 2, so minus 30. So what am I dealing with so far? Minus 46 plus 10, minus 36. Which means that 2 minus 36, which is well down below the x-axis, you will discover an inflection point. And sure enough, put this into Desmos. You should always do it on your practice problems. Visual aids will always help more. Now I'm going to skip this one because it's a difficult one for now. And I'm going to skip, I don't really have to skip that one. And I actually might not. But I'm going to do C instead because C is a lot easier than it looks. C, I can use the chain rule for this because I have two values added up. They're using t, it could be x. The derivative of the first one, so this is first derivative I'm doing, is 1 minus 1 times t to the minus 2, which is minus 1 over t squared. That's what that comes to. And the second derivative, which I'll keep it in this format, the derivative of a number is nothing, so I'm just dealing with this. This is really minus t to the minus 2. I bring the 2 down. And technically I'm supposed to take the derivative of the t over here as well, but I know that's 1. So the minus 2 becomes plus 2, and then up here it becomes minus 3. So I end up with 2 over t to the cubed. That's the second derivative. Go ahead and work it out if you want to do it. So you just do the first and second derivative here, and then this one separately. You'll notice this pattern a lot with derivatives. Now, I want to go back, and you might say, well, what is this? This just looks like a cubic, but it's not. This is actually a rational function. It's t plus 1 over t. If I'm going to add two fractions that aren't the same, I have to put this over t. To get it over t, I have to multiply it by t over t, and I get t squared over t, which means this function is actually t squared plus 1 over t. And I'll put the square in like that. And I have a bad habit of forgetting on my squares. So that's what that function looks like, which means at the top, I don't have an x possible intercept because t squared plus 1 can never be equal to 0. There's no value I can put in here that'll be equal to 0. So it never crosses the x-intercept. I can also see that it probably has an oblique, or does it cross the x-intercept? T squared over t plus 1. No, it can't. I can also tell you that it has an oblique asymptote, and it has a vertical asymptote at t is equal to 0. So that means if to find the oblique asymptote, I take t squared plus 1, and long division t into it, I get t. And I can see that if I take t, I get t squared plus 0. Bring down the 1, and I can see that t can't go into 1. So I know that the equation of this oblique asymptote is y is equal to t, or if you want, y is equal to x. So it's just a normal horizontal. That means, since I know it doesn't cross the x-axis at all, and I'm just going to get rid of that stuff that I've drawn, we're probably talking about something that is zipping along the whole oblique asymptote, comes to a peak and then goes down, and then comes down along the vertical asymptote and then hits the comes close to the diagonal asymptote and then starts going up. And when you look at t squared divided by t, what is t squared divided by t? It's just t. In other words, y is equal to x. So we're really talking about a line, straight line, that was interrupted by the vertical asymptote. Let us see if we can find a max here or a min here using the first derivative. So I'm going to get rid of that graph. I'm also going to shrink this to have a bit of room. I'm going to push this to the right, and I'm going to set the first derivative here equal to 0. So my first step, bring all of this to the other side. I get 1 over t squared is equal to 1. That's no good, though. I can't have t squared on the bottom, so I'm going to multiply t squared over 1 on both sides. It cancels out here. And I'm left with t squared is equal to 1 for the first derivative. If I take a square root of that, I'm left with t is equal to 1, or t is equal to minus 1, which means when t, or x, is equal to 1 or minus 1, I will find a max or a min. So now I have to plug that back into the original equation. 1, if I plug it in, I get 1 plus 1 over 1, which is 2 over 1. So that means the coordinates for this one is 1 comma 2. And then when I plug this one in, I get minus 1 squared plus 1 is 2 over minus 1. So this one is minus 1 comma minus 2. That tells me a lot. That tells me on the left side of my asymptote, and which also happens to be my y-axis, and I'll just put it right close like that. That means on the left side here, all my values are going to be negative, and all my values over here are going to be positive because I know it never touches the x-axis. I also know we're dealing with a diagonal asymptote because t squared is 1 degree higher than t, which means that I'm dealing with something that comes like a straight line here. See if I can do it justice. Something like that. And right here at minus 1 comma 2, minus 1 comma minus 2, I will have the min, and then I will have something similar on this. The only thing you ever have to check here is, does it ever cross that asymptote? So the other point I've discovered here is 1 comma 2. So the only other question is, does it ever cross the diagonal asymptote, which is equal to t? So does this equation here ever equal to t? You can see when you bring the t up, you get t squared plus 1 is equal to t. Is equal to t squared, rather. When you bring the t squared over to this side, you get 1 is equal to 0, which tells you it does not ever cross that line. So it never crosses, and it never crosses the x-intercept. So right there you have a very good idea of what this graph looks like. Now you can also set the second derivative, which I've determined is 2 over t cubed, to 0. So when is t over t cubed equal to 0? In other words, do we have some inflection points? And we can immediately see when the t cubed comes over here, we don't, because the 2 ends up equaling to 0. And even if we flip our fractions and t cubed over 2, which technically we shouldn't do, and multiply by 0, you might say, well, when t cubed is equal to 0, it happens except that the asymptote. That's why you can't flip it. But essentially, when I make the second derivative equal to 0, I don't get an answer, which means there's no inflection point, which actually makes sense. So I'm going to put t squared plus 1 over t into the graph. I'm going to make it equal to f of x. I'm going to just use x squared. Plus 1 over x. And I'm also going to do it in the original form, which is t plus t to the exponent plus 1 over t, right? Or let's make it g of t. There you go. And you can see that they are indeed the same graph. So that was just to show you. Now, if I take the first derivative and set it equal to 0, I will discover the min-max values. And sure enough, it's when f is minus 1. So I'm going to do minus 1. Come on. I'm going to do minus 1, comma minus 2, and label it. And you can see that's the max. And I'm going to do 1, comma 2, and label it. And you can see that's the min. You can also find the second derivative. What is the second derivative when we're at minus 1? And you'll discover it's negative, which proves that is a maxima. And when you set it to 1, it's positive, which proves that's a minimum. And when you do the first derivative of 1, you can see you get 0, which proves the slope, the tangent of the slope is 0 there. When you do minus 1, you also get 0, which proves it's a max or a min as well. You can see we predicted quite well what this line would look like. Now, here's where the problems begin. Oh yeah, let's see if there's a point of inflection. So this is the... Oh, we already determined there's no point of inflection. So let's see, again, if the second derivative of x is equal to 0. And we can see that nothing happens. And I'll change its color just in case to green. You can see that no line is drawn because there's no point of inflection. Great. Let's look at what this graph is here. So I'm going to get rid of all that. You can see that that one was easier than it looked. This one is clearly a number over an x squared plus 48. But I want you to analyze it carefully. This number up top is always positive, isn't it? Can you ever have a negative number down here? You can put negative values of x, but as soon as they're squared, they're positive, and then 48 is added to it. So it's always going to be a positive over a positive, which means this graph never, ever, not only is it always above the x-axis, it never reaches the x-axis, because there's no possible result of 0 here, no matter what x I put in there. Why do I think it's a hump? I just know the history of these graphs, but let's take the derivatives to see if there's a hump. Now, you can use the quotient here. I don't mind using the quotient, except I think it's a bit of a waste of time. I would rather bring this up like this, and I'm just going to keep this graph. Yeah, I'm just going to keep, there we go. And it's multiplied by this thing to the negative 1. So the product rule, which I now prefer to use, says you take the derivative of this times that, plus the derivative of that, which is 0, times this. So since that's 0, it doesn't matter. So we can ignore the second part and just do the first part. So what's the derivative of this? I have to do the chain rule and then take the derivative of the interior. So I know the derivative of the interior is 2x. What's the chain rule? The minus 1 comes out front, becomes minus 1 times 25, so minus 25. And this becomes minus 2, which essentially says my whole thing And 2x times 25 is minus 50x, which means my entire first derivative is going to be equal to minus 25x over this whole thing squared. That's what this means. It means it goes to the denominator and you square it. So we'll have to put a thing like that. And you have to remember to put brackets around the whole thing like that before you square it. So that's the first derivative. When we set that to 0 to see if there's a maximum or minimum, we can say, okay, this comes up. I'm left with 25x is equal to 0, which means when x is equal to 0, there's a max or min. Well, that's fantastic, because now we're only dealing with one max or min when x is 0. We plug x is 0 into here, and we get 25 over 48. So that means at the point 0, comma 25 over 48, there is a max or min. But I've already determined the sort of shape, but let's keep it a mystery. I would actually say finding the derivative on either side of this is a faster way. Like since I was 0, I would find the derivative of minus 1 here. To see if it's positive on the left and negative on the right for maximum. I think that would actually be faster. So I get 25 over minus 1 squared plus 48. So it's 25 over 49. And that's clearly positive on the left side when I take minus 1. So that means there's a positive slope here. When I take to the right side, which is 1, I get 25. Oh, that's going to be interesting, right? Because I've determined that it's positive no matter what I take. Oh yeah, I've got to use the derivative. Sorry. When I take minus 1, which is to the left, I get minus 25x, minus 25 rather. And when I take minus 1 here, it becomes 1 plus 49 squared, so it doesn't matter. The whole thing becomes negative, right? So that means, oh, that's interesting. That means it's a negative derivative on the left side, which means it should be a minimum. Okay, that's interesting. And when I take it 1 on the right side, the first derivative becomes 25 over whatever. This is positive. Becomes positive. So it's going, oh yeah, sorry. Yeah, no, that's weird. So that's saying this actually, it's negative here and positive here. So it's saying that it's actually a min. I don't think so, though. Let's look at what happens when these numbers get huge. I get 25. Oh, no, I should look over here at the original graph. I get 25, and as x gets positively huge, it becomes a small number. If I take negative infinity, it becomes a small number. So I'm almost certain that should actually be a maximum. So that means my first derivative is not giving me the results I want. Why is that? Well, let's take the second derivative. The second derivative is more problematic because now you have to take the quotient rule. So we're going to just forget our min-max point for now. And we're going to take the second derivative. For this, you're going to need the numerator as a function, which is 25x. Maybe it was minus 25x. Hang on, minus 1. Ah, thank you. That's where I'm screwing up. It wasn't 25x. Remember, the minus 1 came down in front? It's minus 25x. So that means minus 1 will create a positive slope on the left and a negative slope. And positive 1 on the right will keep a negative slope. So it is a max. Good thing I remembered that negative, otherwise I screwed it up. Now, to take the second derivative just in case, and the reason I say the first derivative is faster is because you can see how hard it is. This is the function up top, and again, I think it's deleting the negatives when I go back one step. And the derivative of that is minus 25. The function on the bottom is x squared plus 48 squared. So that's just the function. The derivative of that is 2 times x squared plus 48 times the derivative of what's inside, which is 2x. So the whole thing becomes 4x. Great. Now we have the derivative, we have the main function and the derivative of the denominator function. Now we've got to use and you can see how hard this is. Now we've got to use the quotient rule, which says you take the function of the bottom, you multiply it by the derivative of the numerator, you subtract the function of the numerator, so I got a negative 25 is going to become positive, and you multiply it by the derivative of this squared is in the wrong spot. The squared should be over here. There we go. So that's what I get. So I got to do, you can see how expanding this would be hell, and it's also all over the denominator squared, which becomes that to the 4. You can see how a pain in the ass that is. However, we know that x is equal to 0 when the maxima occurs. So we can just put in 0 here. We get 0 plus 48 squared times 25, times minus 25. So we're dealing with a fairly good sized number, and it's going to be positive. Over here, when 0's x, everything disappears. Doesn't matter if it's added here, it gets multiplied by 0 and 0. So this right side doesn't matter. So I'm going to get a big number, and when 0's down here, I get 44 to the 4. So the whole number becomes positive tiny. Go ahead and put it in your calculator if you want. And because it's, or does it become positive and tiny? 0 squared, 48 squared minus 25. It should become negative and tiny. Oh, because it's multiplied by negative 25, not added. So it's multiplied by negative 25, so it becomes a negative number up top. Then divided by a massive number, it becomes negative and tiny. Go ahead and put it in your calculator. You can go ahead and do this with x, but you can see what a pain in the butt this is. To figure out the inflection point, we have to resolve this, subtract it all, and figure out where the reflection point is equal to 0. And you know what? There's probably, I think there is going to be inflection points, which means we have to expand this. So that's x squared times x squared. That's x to the 4. Plus 48 times x squared plus 48 times x squared, which is 96 x squared. Then we have to take the square of 48. Oh, it's just nightmares. You can see how easy it would be to make mistakes. So you get plus 23304 plus 2304, and all of it is going to be multiplied by negative 25. So I'm left with negative 25x to the 4. What's 96 times negative 25? Negative 2400x. And what's 25 times plus 2304? Negative 57,000. Let's try that again. I don't think that's right. Yeah, it's actually, I think it is right. Negative 57. Oh, well, I've got to do it again. Anyway. 2304 times 25, and then I'll just change the symbol. Negative 57, 600. So that's all this left expanded. Keep in mind this negative here becomes a positive right there. So we can just change that to positive and not worry about it. 25 times 4x squared is 100. 5x times 4x is 100x squared. Then when I multiply it through this, I get 100x to the 4 plus 4 times 96, 200 minus 8, 192 x squared. Woof. So that's all getting added. And it's all over that denominator. Now you don't have to worry about the denominator so much. So that means I'm going to get all of this. And don't forget I've got a 4 up here and a 2 up here. And it's all being added to this if I got it right. And you can see how hellish it can be. I even think I forgot a multiplication somewhere in there, because I'm pretty sure the x squareds are going to cancel out. So instead, what I'm going to do is I'm going to ask it the Symbolab, because I'm quite sure I made a small technical error. So you can always take your Symbolab and verify your results. And you can simply ask Symbolab to expand the top for you. You just had to hope you wrote it all down correctly. Or you can ask him just to take the derivative of your first derivative. You can see this whole thing gets crazy. And I'm just going to leave the denominator out of this, and I'm just going to click go. And it gives me this. So again, I don't think that's correct. So that tells me that I probably made a whole mess of the second derivative anyway. So you should go back, figure out your first derivative, and ask, and that's what I'm going to do right here. I'm going to ask Symbolab to take the first derivative, then the second derivative. Do that, and I'm going to say, find me the derivative of 25 divided by x squared plus 48. And I'm going to ask him to find the first derivative and see if I got it right. I did not. Didn't I? Oh yeah, no, I did. Although I think I had 25x, so I forgot to multiply it by 2. So you can see I got the first derivative wrong, which didn't help my cause. This is the first derivative, and I think it's because I mixed up my actual function with the derivative. And then if I take that and find the second derivative of that, which is just the derivative of the derivative, it will tell me, yeah, so this is a much easier version of it. It's pretty close, but you can see that this is the second derivative, and setting it to 0 is a lot easier than this is a good example of when the original derivative test, which is what I was saying, is a lot easier than calculating and expanding all your second derivatives. But when I set that second derivative to 0, this obviously disappears. This 150 doesn't matter, so the question is, when is minus x squared plus 16 equal to 0? It's when minus x squared is equal to minus 16, or if you want, when is x squared equal to 16? And it's at minus 4 and 4. And then I would plug this back into the equation, and I get 25 over 416 plus 48, 54, 64. So at 25 64ths, 4 comma this and minus 4 comma this, I will find an inflection point, which means I'm dealing with a hump like that. So I'm just going to put this into decimals, which is probably what you should do to start with anyway. Helps if you make it f of x instead of y. And I get 25 divided by x squared plus 48. Can't quite see the hump, but it's there. And if I take f of 0, it's definitely going to be there, 0 comma f of 0 is there. And then if I take 4 comma f of 4, I'll see the inflection point, and minus 4 comma f of minus 4, I'll see the other inflection point right there. Just to verify, the f of x, where f of x is equal to 0, is indeed at the 1 spot, and where f double prime of x is equal to 0 will be where the 4's are. So with the help of Symbolab, I was able to find that. But you can see how many mistakes you can make taking the second derivative of a quotient, because the expansion and finding the common groups can take a long time. So hopefully when your teacher gives you a test, it's not too bad. Now, looking at this, this is, to me, and remember that this is cubed, this is a cubic. And because the same coordinate is cubed, I know that probably at 3 comma 8, we're going to have a slip and slide. So my first derivative is going to tell me that there's a max, but my second derivative, I'm sure, is going to be equal to 0 when I have 3. And this just helps to know what that is. But let's take the first derivative. First derivative is just the chain rule times what's in the chain rule. So we'll get 3 times x minus 3 to the 2. The 8 disappears. And the internal derivative is just of x minus 3 is just 1. And the second derivative is 6 times x minus 3, which is a line, 6x minus 18. So that's the second derivative. And that's the first derivative. Now, it's clear to me, setting the first derivative to equal to 0, the only way that can happen is when x is 3. And when I plug 3 in here, I get 8. So sure enough, it tells me that there's a max or a min at 3 comma 8. The second derivative, I would plug in that 3, and I get 18 minus 18, which tells me, uh-oh, that's equal to 0. There's a problem with this max or min. If you take the slope just to the left of 3, if you use 2 here, you get 2 minus 3, which is 1 squared, times 3. I get a positive slope just to the left. If I take 4, I get 4 minus 3, which is 1. I get a positive 3 slope on the right as well, which tells me I'm dealing, as I suspected, with something like that. And the example they're putting here is to show you that the second derivative equaling 0 should make you investigate further. Now, just as there's no point in setting it to 0 because it comes out to 0, which tells me that there's a problem anyway. So there's no need to find the point of inflection when the maximum point is giving me 0 as well. There's the point inflection happens to be what should be the max min. And sure enough, when you put it into Desmos, and you get x minus 8 cubed, or 3, was it x minus 3 cubed plus 8, you will indeed see what we were talking about. When you do 3 comma f of 3, you can see that point of inflection that we're talking about. When you set f of x is equal to 0, it gives me that point of inflection. And when you set f of x, double prime x to equal to 0, it also gives me that point of inflection. And that just comes from knowing that a graph of a cubic that has the same factor 3 times will create that slip and slide aspect. So I could have deciphered this without the graph. Now, second derivatives can have a lot of painful processes, and it all depends on the function. These are easy. These are easy. This will cause you headaches because a square root is the same as to the power of 2. And this will also provide, well, it'll be easy because there's no squares on the t's. So they're saying determine the value of the second derivative of each point of x that they give. So they give different points of x, and they change x to t and w. This first one I can do. I think I'll have to stop at part 5. but this first one I can do. I'll try to do the easy ones. First derivative is 6x squared minus 10. Second derivative is 12x. So they want to know what the value is positive or negative when x is 2. When x is 2, it's positive. So that means, let's find what it is when the first derivative is. When the first derivative is 2, we get 4 times 6 minus 10, we get 14, which is positive. Which means if the first derivative is positive, and the second derivative is positive, positive would indicate a min. So that means we're on this side going up. Now it could be like that as well, but we're going to be on the right side of a minimum point or a rising point. Sure enough, this is a cubic. I don't know if there's a factor to it. There's not. We can put it in quickly. 2x cubed minus 10x plus 3. Yeah, so I think we're dealing with that. And if I take the first derivative at 2, I get 14. If I take the second derivative at 2, I get 24 as expected. If I take the value, or show the value of that, we get that. And it's clear, as I said, it's on the right side of a minimum point. Could have been a slip and slide as well. And that is because both the derivative and the second derivative were positive. The second derivative tells me it's just part of a minimum curve, and the first derivative tells me the slope is, the line is going up, positive. All right, what about the next one? This one. Okay. Just remember that the second term is simply this, and that the line itself is this. I'll let you figure out how I got there, which means we're dealing with a vertical asymptote. We're not going to have any kind of, let's see, as this approaches positive infinity, this approaches positive infinity, we're up to positive infinity. As this approaches negative infinity, divided by negative infinity, it approaches negative infinity. As we approach 0, what happens on this left side when we're like -1? We get -1 minus 1, -2 over -1. We're way up here. So we're talking, I think, something like that. Oh, it might go. I don't know how the shape goes, actually. If I look at it generally, just divide the two. I'm talking about a parabola, so I'm probably looking at something that's trying to be a parabola. It reaches the asymptote and either rips down here, and then on the other side it does something like this and tries to continue its normal parabola, or vice versa. Since I've determined that if I take negative infinity here, I get divided by negative. I get a negative divided by negative. I get a positive, so it's way out there. If I take positive infinity, so it's way out there. I just have to figure out what happens when it's right near 0. So when I take -1, I get -1 minus 1 over -1. So that's +2. So I believe this left side is actually going to be the one to zip up the parabola. And then when I take this 1, put it into the formula, I get 1 minus 1. Oh, so that means I cross the intercept at 1, which tells me that on the other side, I'm probably doing some weird, probably coming up, going through, and then continuing on. So I'd have to take a really small value to see what it's doing just before that, like half. So at 0.5 cubed, 0.5 to the 5, I get like 0.125, minus 1, I get minus 0.75, over 0.25. So yeah, it's way down negative as it gets closer to that. Let's ignore that and go back to the derivatives. This is the best way to take the derivative. The first derivative is going to be 2x minus 2, minus 1, which becomes plus 2 over x squared. Okay, so that's the first derivative. The second derivative, which is that, will become 2, and then it's x minus 2 with a 2 in front. So it's going to become minus 4 over x cubed. You might say, how did you do that? Okay. If this is the first derivative, let's go right back. If this is the rewrite of this, that's the first part you have to understand, is that 1 over x is the same as that. And I'm just preserving the minus in the middle. For this, you can do I call it the chain rule, but I think they call it the product rule in the book, which means you just take the derivative of that, which is 2x. What's the derivative of this? When you bring the minus 1 down in front, you multiply it by the minus 1 in front, so you get plus 1. Then this lowers by 1, so it becomes minus 2. But what is x to the minus 2? It's the same as 1 over x squared. Boom. That's the first derivative. What's the second derivative of this? Well, the derivative of 2x is 2. The second part is the same as this. What happens when I bring the minus 2 out front and multiply it by the plus 1? I get minus 2. This lowers by 1 down to minus 3, which really is just x cubed at the bottom. So I end up with minus 2 over x cubed. And that's the second derivative. Now they've given me a value of minus 1. So it helps to go back to the original graph. So here's the first derivative, here's the second derivative, and here's the original graph, and figure out each point as it's going on. So when I put in negative 1 for here, I get negative 1 squared minus 1 over minus 1, which becomes plus 1. So I get 2. So it's negative 1 comma 2. And as I've already discovered, I believe the left side is doing that and hugging the asymptote. It's also not crossing the x-axis. So I believe it's doing that. Now, if I believe it's doing that, it's either on this side or that side of the bottom part of it, and I think it's on the right side. So I'm going to get a plus and a plus for the first derivative, and I believe I'll get a plus for the second derivative. So now I take the minus 1 and put it into the first derivative, and I get minus 2 plus 1. Oh, I'll make sure I got the derivative correctly. Yeah. So I get minus 2 plus 1 over 1. And so that means minus 1. So that means my first derivative is actually going down. Okay. Then if I take minus 1 into the second derivative, which is here, I get 2 minus, what's minus 1 cubed? It's minus 1. What's minus 2 divided by minus 1? It's plus 2. So I get 2 plus 2. I get 4, which means it is definitely a minimum, because plus second derivative means I'm at a minimum. But because I'm at a minus slope, it means I'm on the left side of the minimum. So let's have a look. X squared minus 1 over x. X squared minus 1 over x. Sure enough, it's exactly as I described. It's a parabola that got interrupted by the asymptote. You can also see that the x-intercept is indeed there, and then as it goes down, it goes into negative infinity, positive infinity up here, positive infinity up here. And you can also see that that's the min point, and so the point in question, minus 1 comma f of x. Okay, it won't let me do it like that, so I'll just get rid of everything and start again. Minus 1 comma f of x. Why won't you let me get rid of it entirely? Minus 1 comma f of minus 1. There we go. That's what I was doing wrong. There. If you zoom in, it is indeed to the left. I thought it would be to the right, but the first derivative showed me it was sloping down. If you take the first derivative at minus 1, you will indeed see minus 1, like we said. And if you take the second derivative at minus 1, you will see a positive 4, as we also said. So it tells you a lot about what's coming up on the curve, or what part of the curve it's in. Oh, I should also see, if, just for fun, if there's a point of inflection. So when is the second derivative equal to 0? And we can see there's indeed a point of inflection as it goes through the x-axis. So this side of the curve was concave up, and then this side of the curve is concave down. Which means if I was to take a second derivative on this side, I'll get negative values, and a second derivative on this side, I'll get positive values. Let's see if that's true. Let's take a second derivative at 2 and a second derivative at 0.5. So second derivative at 2 should be positive, and it is, and second derivative at 0.5 should be negative. Oh, 0.5. Oh, it should have been negative. Oh, I accidentally put in that. No. 0.5. We'll just do it like that. Yeah, I get negative. And sorry, I put it in the wrong one over here. This was the first derivative. So let's go back and put it in for 2. And indeed, oh, I get positive for 2. Yeah, and I should get negative for 0.5. Yep, good. So that is indeed a point of inflection. All right. What about this one? This one I'm going to skip. That one's going to give you headaches. This one, not so much. I'll do this one next video. This one, not so much. It's a lot easier than you think because it's got a lot of zeros in it. So, first derivative, we have to do the quotient rule, which means we should take each function, and at the bottom is going to be left with t minus 4 squared. So as a denominator, I'm going to have t minus 4 squared. Right. At the numerator, it's going to be the first function. I wish they included brackets. It's going to be the denominator function times the derivative of the numerator, which is 2. Then it's going to subtract, and it's going to be the second function, or the numerator function, times the derivative of this new denominator function, which is 1. So it's just going to be minus 2t. So for the first derivative, I can see that this times 2 will be 2t minus 8 minus 2t. So the first derivative is a nice clean 8 over t minus 4 squared, which makes our life easy. So that's the first derivative. If you take the second derivative, it's the same rule. You take the denominator and you square it. And here it gets a bit more complicated. You take the first denominator and multiply it by the derivative of the numerator, which is 0, so it disappears. Then you just have minus times the numerator times the derivative of this, which is 2 times t minus 4. And then the derivative of inside that is just 1. So minus 8 times 2 is minus 16. So times t is minus 16t. And minus 4 times minus 16 is plus 64. So that's the numerator for the second derivative. So to type it out instead, because that's really my problem when I'm doing these lessons, I get minus 16t plus 64. Hopefully I did it right. You can always use Symbolab. So that means they're asking me what's going on at this mark. Maybe we should understand this graph a bit. Do the t's match in exponents? There we go. Whoop. Do the t's match in exponents up above? Yeah, they do. If I take the coefficient, divide by the coefficient, I get y is equal to 2 as a horizontal. Right here, y is equal to 2 as a horizontal asymptote. And I can see a vertical asymptote will exist when x is equal to 4. Sorry, when x is equal to 4, t is equal to 4, which means I have another vertical asymptote right here when x is equal to 4. Other than that, this is a very ordinary rational function, which means something's going to happen here. It's either here and here, or it's here and here. It all depends what happens in, let's say, 5 land. If I put positive 5 in here, I get 10 and 1, so 10 over 1. So it's clear 5 is up here, so it's going like that and like this. Now, the question is, they want to know what's going on at t minus 2. So I'm going to say t minus 2 is somewhere over here. We're going to be approaching the y-axis. This slope is clearly going to be negative. And because if I look at this, it's like a maximum, then the second derivative is going to be negative 2. So I'm going to put minus 2 into the first derivative. I get 8. 2 minus 4 is minus 2. Squared is plus 4. I get 2. I get a positive slope. Let's try that again. Minus 2 minus 4. Minus 6. Yeah. Minus 6 squared is 36. So I get 8 over 36, but still positive. Interesting. I hope I did the derivatives right. And because my instinct says that's not right. So this is, again, I'll take Symbolab, and I'll take 2t, t over minus 4. Derive 2t. T over t minus 4. And I'll say go. And I got 8 over t minus 4 squared. So I got it right. Oh, no, I forgot the minus. And that's just a good example of what can happen. There's a minus here, so clearly I forgot the minus. And that's right, because it was minus 8. Which makes sense, the first derivative will come out as minus. And let's make sure we got the derivative correctly of the second one. Derive minus 8 over t minus 4 squared, which I believe is the derivative. And did I get the second derivative right? No, I got the second derivative wrong as well. This is the second derivative. Just goes to show you, if you screw up once, or one thing, it screws it all up, which is unfortunate because this was not a hard derivative to do. So here's the second derivative, and this is the first derivative. So now when I put minus 2 into the first derivative, I get minus 8 over 36, which is clearly a negative number. And when I put minus 2 up here, I get a positive number, but this is cubed, so it's minus 6 cubed, which will be a negative number. Positive divided by negative will be negative. So both the first derivative and the second derivative come out negative, which makes sense when I use Desmos because the graph is exactly as I expect it to be. I'm going to put my y is equal to 2, my x is equal to 4, and I'm going to put my calculations as x, 2x divided by x minus 4 squared. Squared, or just x minus 4, x minus 4. And sure enough, you get the exact drawing I expected. Just I spazzed out, and at the point minus 2 comma f of x, you see the point I expected. And you can also find the derivative at minus 2 is negative, and the second derivative at minus 2 is also negative. So, taking the first derivative and second derivative, you have to be very careful on these complicated ones. Let's go back and see where I made a mistake. So the first derivative is the numerator times the derivative up top. So that's 2. There's the minus 8 right there. Minus the derivative of the denominator, which is just 1, times that. So you can see 2t minus 8 minus 2t, it should have been minus 8. So there's my first mistake. And all over t minus 4 squared. So I shouldn't be screwing up for those that badly. Now let's see if I can do the second derivative. The second derivative is, it's going to be, surprised it's a cube here, but it's going to be, oh, I think they cancel out. So it's going to be the bottom squared, which is to the 4. And on the left, I'm going to have the actual, oh, I forgot to expand it, squared, times the derivative of 0. Oh, so it just disappears. Minus 8, so that's the problem, plus 8, times the derivative of this, which is times 2, times t minus 4, that's the cancellation, times the derivative of inside the bracket, which is just 1. These cancel. I get 3 here, and 2 times 6 is 16. So the problem is I expanded it and kept it as a polynomial up top. So you can see how that becomes 16 when this cancels with that and brings it down to 3. So the second derivative was much easier than I thought, and all that screwed it up, well, there's a few things I screwed up. I didn't cancel, but also this screwed it up quite a bit. All right, clearly I'm tired. I'm going to stop. Glad to correct a couple things.